Hello students, welcome back to the series Coordination Chemistry. In this module, we will be continuing the theories of coordination compounds. In the previous classes, we were discussing about the theories of coordination compounds and different theories, that is crystal field theory, etc. And this in the crystal field theory, we have already discussed about the crystal field splitting of octahedral complexes in the octahedral field, crystal field splitting. And now in this class, we will be discussing about the crystal field splitting in tetrahedral complexes. And in the tetrahedral complexes, 4 ligands are there. We have 4 ligands which are arranged at the 4 corners of a cube. So, they are considered to be present in the alternate corners of a cube. And the molecule here is not symmetric. See, the cube, in a cube, we have 4 ligands that are arranged at the alternate corners. And the molecule is not at all symmetric. But in the octahedral molecule, the crystal, the molecule was symmetric. That is why we have used their T2G and EG. G means gerade and U means ungerade. But in this case, since the molecule is not at all symmetric, you can't use G or U. So, we have to represent T2 and E, not T2G and EG. So, G and U should be avoided in the case of tetrahedral complexes or tetrahedral crystal field splitting. And see, this is the splitting of d orbitals in the tetrahedral field. You can see the d orbitals in the free ion, and in a spherical crystal field, it is the average energy is being raised. And in the tetrahedral crystal field, the d orbitals will be splitting as follows, that is E and T2. You can see that E will be having lower energy and T2 will be having higher energy. And we know that we have 2 E orbitals, or in the octahedral field you have seen that EG. They were dx square minus y square and dz square, and T2 will be 3, that is dxy, dxz and dyz. And that those energy that these orbitals, that is T2 orbitals, will be having greater energy and E orbitals will be having lower energy. And you can see the difference between the splitting, that is delta T. In the case of octahedral field, it was delta O, that is delta octahedral. But when we are discussing about the tetrahedral field, we have to replace O with T. So, it is delta T, and it is the energy difference between E and T2 orbitals. And you can see the Barry center at the middle. In the crystal field splitting energy, the energy difference between the T2 and E is termed as delta T, and the relationship between delta T and delta O can be represented as delta T equal to 4 by 9 delta O. See, when we look at the relationship, you can see that delta T is always less than delta O. That is, the crystal field splitting in tetrahedral field is always less than crystal field splitting in octahedral field. And what are the reasons for that? There are 2 reasons. That is, in the case of tetrahedral field or in the tetrahedral complexes, there are only 4 ligands present in the tetrahedral complexes. But in octahedral complexes, you have 6 ligands. So, the number of ligands in tetrahedral complexes is always less when compared to octahedral complexes. When the number of ligands decreases, obviously the splitting will be decreasing. That is, the repulsion will be less when compared to the octahedral field. In octahedral crystal field, you have 6 ligands, and due to the presence of these 6 ligands, the splitting will be greater. But in tetrahedral field, you have only 4 ligands. So, since 4 ligands are present, that splitting will be much less when compared to delta O. And the second reason is that there is no direct interaction of these ligands with the metal d orbitals in the case of tetrahedral field. But in the case of octahedral field, you have already seen that these orbitals are coming towards, they are coming along the axis, and so along the axis d orbitals, that is dx square minus y square and dz square will be experiencing a greater repulsion. So along the axis there is a direct contact of these ligands with the metal d orbitals in the case of octahedral field, but in the case of tetrahedral field there is no direct contact. That is why the repulsion is much less when compared to the octahedral case. And when we look at the spin complexes, what is the peculiarity of the complexes? These tetrahedral complexes are always high spin complexes, but octahedral complexes may be high spin or low spin. And why it is so? See, high spin complexes means the electrons will be occupied, since the delta T is much less, the electrons will be going upside, in the greater energy. For example, if we are filling the electrons in the D4 case, that is first 3, after the filling of first 3 electrons, the 4th electron will be moving to the upper state, and such complexes are also called as high spin complexes, because spin is more in that case. And low spin complexes means there will be having a greater delta, in the case of octahedral complexes, if we are representing as delta O, that delta O will be much higher. So that electron, the 4th electron, may not be able to go to the higher Eg level. Such complexes are called as low spin complexes. But when we look at the tetrahedral complexes, all tetrahedral complexes are high spin complexes. The reason is that delta T is very much less, or pairing energy is more in the case of tetrahedral complexes. See the crystal field splitting energy, stabilization, CFSE, that is crystal field stabilization energy. We have already calculated in the case of octahedral complexes different from D1 to D10, we have already calculated the values. In this case, you can calculate the values of this CFSE from D1 to D10. How to calculate is already discussed in the previous classes, that is when we are going to the D1 case, that is 1 electron in the d orbitals, then that electron should be, we have already seen the crystal field splitting. If in the D1 case, if it is a D1 case, 1 electron will be occupying this dx square minus y square or dz square. So that electron should be multiplied with the stabilization energy, that is minus 3/5 delta T, means that is minus 0.6 delta T. So 1 into minus 0.6 delta T, that is calculated, and so 1 into minus 0.6 delta T means it is minus 0.6 delta T. It is the case of D1. So when we are moving to the D2 case, that is 2 electrons in the d orbitals, means 2 electrons will be occupied in the E only, and the stabilization energy is minus 0.6 delta T. There are 2 electrons, so 2 into minus 0.6, what is the answer? It is minus 1.2 delta T. And coming to the third case, that is D3, means 3 electron in the this T2 or E orbital, but 3 electrons will not occupy in the T2 orbitals, E orbitals, because tetrahedral complexes are always high spin complexes, means after the second electron, the third electron will be moving to the T2 orbital, higher orbital. So we have to calculate 2 into minus 0.6 plus 1 into 2 into minus 0.6 plus 1 into plus 0.4. So what will be the case? The answer will be minus 0.8 delta T. How to calculate all those things we have already discussed in the previous module, that is in the octahedral crystal field splitting. And so when we are substituting that D1, D2, D3, D4, D5 up to D10, you will get the values like this. See the case of the D5 case, that is 5 electron in the d orbitals, means this tetrahedral complexes are always high spin complexes, means the after second electron, third will be moving to the T2, fourth will be in the T2 and fifth also will be in the T2. So, there is a symmetric arrangement of the electrons. In the E orbitals we have 2 electrons, in the T2 orbitals we have 3 electrons. So, while calculating you will get the answer as 0. And also when we look at the CFSE of D10 complexes, D10, in the case we have 10 electrons in the d orbitals and 4 electrons will be there in the e orbital and 6 electrons in the T2 orbitals, and after summing up you will get the answer as 0. And this is how you can calculate the CFSE of tetrahedral complexes. And now you can take the examples. See the how to calculate the CFSE of NiCl 4 times 2 minus. When we look at the oxidation state of nickel, it is Ni2 plus because we have 4 chloride. So, it is minus 4 to become minus 2 means nickel should have the oxidation state of plus 2. So, it is Ni2 plus state and it is a D8 system, means nickel is having the electronic configuration 3D8 4s2, and in the case of Ni2 plus, that 2 electrons will be removed from the s orbital. So, 4s0 3D8, that is the case, or you can say that it is a D8 system. And this chloride Cl minus is a weak field ligand that we have already discussed what are weak field and strong field ligands. And since Cl minus is a weak field ligand, we have the hybridization of nickel as sp3 hybridization, that is it has got a tetrahedral geometry. And while we are calculating the CFSE of this complex, you have the nickel D8 system. So, 1, 2, 3, 4, 5, 6, 7, 8 electrons in the d orbital, and in presence of the tetrahedral field they will be splitted as E and T2. And while filling the d electrons, 8 d electrons in the E and T2, see first electron will be in the E, second will be also in the E, third will move to the T2 since this tetrahedral complexes are high spin complexes. So, 1, 2 and 3, 4, 5, 6th will be going here, 7th will be here and 8th will be here. Okay. So, this is the case, and now we can calculate the value that how many electrons are there in the E orbital. We have 4 electrons, 1, 2, 3, 4. So, 4 into what is the stabilization energy of this? It is minus 0.6 delta T. So, 4 into minus 0.6 delta T. And how many electrons in the T2? We have 1, 2, 3, 4. 4 electron in the T2 also. So, 4 into what is the destabilization energy? It is 0.4 delta T. So, 4 into 0.4 delta T. After summing up, you will get the answer as minus 0.8 delta T. This is the way to calculate the CFSE of NiCl 4 times 2 minus. And take another example, that is COCl4 2 minus, that is a cobalt system. Cobalt is having an oxidation state of CO2 plus, that is chloride we have 4 Cl minus. So, minus 4 to become minus 2 means cobalt should be in the plus 2 oxidation state, or you can say that it is a D7 system. How it becomes a D7 system? Cobalt is having the electronic configuration of 3D7 4s0. Since the CO2 plus means the 2 electrons will be removed from the 4s. So, 4s0 3D7, or you can call it as a D7 system. See the crystal field splitting, the d orbitals in the free ion state, that is how many electrons? D7 means 1, 2, 3, 4, 5, 6, 7. And in the presence of the tetrahedral crystal field, there will be splitted into 2, E and T2. How to fill? The 7 electrons 1, 2, 3, 4, 5, 6 and 7. And now you can number how many numbers are there in the E orbital. You have 4 electrons. So, 4 into the stabilization energy is minus 0.6 delta T. So, 4 into minus 0.6 delta T. How many electrons in the E? You have 3 electrons. So, 3 into destabilization energy is 0.4 delta T. So, 0.4 delta T. After summing up, you will get the answer as minus 1.2 delta T. And this is the way to calculate the crystal field stabilization energy of any complex you can calculate. And now we are moving to another crystal field splitting, that is In the previous classes, we have discussed the octahedral crystal field splitting, and in this class we have started with the tetrahedral crystal field splitting. Now moving to the tetragonal complexes. Tetragonal. Then what are tetragonal complexes? See, if the ligands lying along the z-axis are at a different distance from other ligands than the other ligands. See the case, this was an octahedral complex, but the peculiarity is you can see that the two ligands are different from other 4. Two ligands, in the first case, that is elongated case, you can see the two ligands are different from the other 4. Or you can consider a compressed situation, that is in that case also, second case also, you can see that the two ligands are different from other 4, that is it is somewhat compressed. So these two are called as tetragonal complexes, means there is some kind of distortion from an octahedron, regular octahedron. So if the ligands along z-axis are at a different distance, the ligands along z-axis means these are the ligands along z-axis, these two and these. So these two ligands are at a different distance from other ligands, then that complex is said to be a tetragonal complex. And this tetragonal crystal field splitting is also different, because the metal ligand distance is different in this case. Both the cases you can see. See, you have the two cases. In this case I have already told that elongated case and compressed case is there, and now we can consider the tetragonal elongation. That is the first case, means the z-axis, the ligands along the z-axis are being elongated, or they are at a greater distance when compared to the other 4. In that case, you can see that the orbitals which are lying along the z-axis will be experiencing a lower repulsion. So which are the orbitals that lie along the z-axis? It is dxz, dyz and dz square. So these 3 orbitals will be having a lower energy. So this is the crystal field splitting. Here in this case you can see that these are the T2G orbitals. How many T2G orbitals are there? We have 3 T2G orbitals, that is dxz, dyz and dxz, dyz and dxy. And in the T2G orbitals, how many are having the z component? 2 are having the z component, that is dxz and dyz. So in the case of the elongation, that is the tetragonal elongation, those orbitals will be having still a lower energy. So that is why the dxz and dyz is occupying a very low energy when compared to dxy. And so this is the case of T2G orbital. Now coming to the EG orbitals. In the EG orbitals we have 2 d orbitals, that is dx square minus y square and dz square, and among these 2 which is having a z component, it is dz square. And I have already told that this the orbitals which are lying along the z axis will be lowering. In the case of the elongation, they will be having a lower energy. That is why the dz square is occupying a lower energy when compared to dx square minus y square, and this is the case of splitting in tetragonal elongation. The only thing you have to keep in mind is that the z component will have a lower energy. That is the thing that should be understood, or that is the thing that should be kept in mind. That is dxz, dyz lower energy, dz square lower energy when compared to the other. And now coming to the other situation, that is tetragonal compression, means the z axis, the ligands along the z axis will be having a greater energy. The reverse is the case. See, these dxz, dyz is lower energy in the case of tetragonal elongation. In the tetragonal compression, it is just the reverse. See the situation, dxz and dyz is having a greater energy, this dxy is having a lower energy. In the case of EG orbitals, the dz square is occupying a greater energy or having a greater energy, and dx square minus y square is having a lower energy. So that is the tetragonal elongation and the tetragonal compression. And now we are moving to the crystal field splitting in square planar complexes. Square planar means how a square planar complex arises. See, when we are considering an octahedral complexes, all the ligands are having the same distance from the metal. If we are elongating the ligands along the z-axis, it is tetragonal elongation. If we are just removing the ligands along that axis, we will get the square planar geometry. And this is the case. This is how we arrive at a square planar geometry from an octahedral geometry. This is a regular octahedron. In this case, we have metal ligand bond distances similar, that is all the 6 ligands are at an equal distance from the metal. This is a regular octahedron, and when we are just elongating the ligands along z-axis, we will get the situation like this. Just removing, you will get these 2 ligands will be removed from the molecule, we will get the square planar geometry. And from this, why I am discussing about how we arrive at a geometry of a square planar complex is that you can actually find out which orbitals will be having lower or which orbital will be having higher energy in the square planar complex. See the situation, we have 5 d orbitals. In the case of square planar geometry, the ligands along z-axis are being completely removed, and then what will happen? When the ligands along the z-axis are completely removed, the d orbitals which are having their which are having their z component will be having a very less energy. See this. The first case is dxz, dyz, that will be having a lowest energy because the z along the z-axis ligands are being removed. And in the case, this is the dz square, means dz square was the d orbital of the Teg orbital. So, it was in the upper state, but in the case of square planar complex, since the z orbital the ligands along the z axis is completely removed, that d orbitals will be having a very less energy, that is dz square will be coming from here to here. That is why dxz, dyz, and just above this dxz and dyz you can see dz square, and then you can see the dxy, means dxy was lying here, it just go up because it will be having a greater energy, or energy will be raised in the case of dxy, and you have the highest energy, that is dx square minus y square. This is the situation of the crystal field splitting in square planar complex. The only thing you have to keep in mind is, in the square planar geometry, the dxz, dyz and dz square orbitals will be having very less energy. When we compare dxz, dyz and dz square, that will be according to the previous order, that is dxz and dyz will be having a lower energy than dz square. This is the case, and here the difference between dxy and dx square minus y square will be the crystal field stabilization splitting in the case of square plane, delta sp. Delta sp means crystal field splitting in the case of square planar complexes. And so, when we consider the square planar complexes, they are usually adopted by the metal ions in the D8 electronic configuration. Means the metal ion in D8 situation will be having the square planar geometry. Means the nickel system Ni2 plus. Ni2 plus means they are having the D8 system. And in the presence of a strong field ligands, that is, if we are having the ligands which are having a greater capacity to pair, or such complexes, such ligands are called as strong field ligands. In the presence of strong field ligands, the 8 electrons occupy the lower 4 orbital. Which are the lower 4 orbitals? See, 1, 2, 3 and 4. In the strong field ligand, these electrons, 4 electrons means 4 orbitals means 8 electrons. 8 electrons will be occupying in dxz, dyz, dz square and dxy. That is 1, 2, 3, 4, 5, 6, 7, 8. The dx square minus y square orbital will be remaining unoccupied. Means, see this delta sp will be greater, and the D8 system means we have only 8 electrons. They will be occupying only up to dxy. This is a case of the crystal field splitting in square planar complexes. We have already discussed how we can identify, how we can group the d orbitals based on the square planar splitting, that is the z square orbital or z component orbitals will be having the lower energy, lowest energy. In the case of tetragonal complexes, we have two cases, the tetragonal elongation and a tetragonal compression. In the case of tetragonal elongation, it is the z orbitals that will be having the lower energy. In the case of tetragonal compression, it is the z orbitals having the higher energy, and that is the case. So, in this class we have discussed about the tetragonal, tetrahedral and square planar crystal field splitting. We have already discussed in the previous class about the crystal field splitting of octahedral complexes, and all these are equally important. And in the next module we will be discussing about the tetragonal complexes or tetragonal distortion in particular, that is John-Teller distortion, which is a very important topic. Thank you all for watching this video. Bye.